Okay. Yeah. So, yeah, as promised in the last class, I will show you one example, and I am taking the example from my paper that I wrote with Keith. Okay, because with sorry, with whom? Keith Ellis. Yeah. So it is better to show some calculation of your own than to taking help from others. Yeah. Fine. So the example I will be telling you is the GG going to Higgs production. So the process is GG going to GH, okay, with top mass loop. So let's call it P1, P2, P3, P4. Okay, L is going this direction, and everything, all momenta, all P's, they are outgoing. Okay. So this is my L minus P1, this is L plus P2, this is L plus P23. Okay. Now I have to calculate the amplitude, which I know at one loop it is sum over box plus triangle plus bubble plus rational term. Okay. Now for there are like triangle loop and one addition, meaning
initial clone.
Oh, so we are talking about this, huh? Yes, this kind of things, right? Yeah, so when I'll cut, I'll take all those diagrams in my diagram. Let me explain how. Okay. Okay, fine. This is my one loop, and I will be starting with the a specific color ordering, that is 1, 2, 3. Okay. Rest of the color ordering I can get it from here. All right. So first I will calculate this box coefficient. For the box, what do I need to know? Suppose if I cut this propagator and this propagator. For box I have to cut this and this as well, but for the timing, suppose I have cut these two propagators. Okay. So then I got two tree level amplitude, okay, which is U bar L minus P1, 1G, 2G, 3G, U L plus P23. Okay, this is the left side diagram, right? Left side of the cut. This is the diagram. The right side of the cut, what do I have? I have U bar L plus P23 M by V. M means empty. Okay. U L minus P1. I have not written anything, just writing the structure. Now I will come to it. Okay. All right. So now I have to glue these two amplitudes. Okay. So now the point is, if you calculate it in the usual Feynman diagram technique. The expression is huge and I cannot write it on the blackboard, it is so long. But if you use BCFW technique, then this amplitude boils down to a simple term. I am writing it what it is. It is basically m u bar L minus P1 gamma r u L plus P23 1 over 1 2 2 3 1 L slash P2 slash and then in the denominator L square minus m square and L plus P2 square minus m square. How this is coming I can show if Vaibhav and Saurabh give me some time. Yeah, okay. But anyway, yeah, what is the question? Huh? Yeah, what is it? Okay, I'll tell you quickly. Let me finish. For the time being, accept this is the amplitude. Okay. How it is coming? Maybe I can tell you later. Okay. Right hand side is very simple. It is already written. Nothing to be right there. Okay. Now I have to now see. So this came with these two cut, left side and right side. Now I want to calculate the box, so I have to cut these two propagator as well. Okay. So if I cut this propagator, then from this amplitude this term is gone, right? Sorry, there was another term I guess. Yeah. So the full amplitude was so this term is gone, this is gone, okay, and I have cut this propagator also, so this is gone, not 0 actually, this is vanished, okay, because I am cutting the propagator, they are on cell, right, an on cell propagator I will throw it out, okay. So once I put the 4 cut, now my result is AL times AR, which is m square by V u bar L minus P1 gamma r u L plus P23 and then u bar L plus P23 u L minus P1, okay, and then rest of the part 1 2 2 3 1 L slash P2 slash 3. This is my result, right, after the 4 cut, okay. Now I have to simplify it. So see, now I can, for simplicity I can fix, okay, so this amplitude is for all plus helicities, huh? So whatever I have written, these are for plus, for minus it is a bit difficult to show in the blackboard, okay. So yeah, now what should I do? Yeah, now see, so I am not fixing any helicity for this propagator, so I have to sum over all the spin. If I do, then this will be basically m square by V trace of gamma r L slash P2 slash plus M L slash minus P1 slash plus M, right, this part, and I am left with this part only, 1 2 2 3 1 L P2 slash 3. Now I know how to parameterize the loop momenta in case of 4 cut. So L mu is alpha P1 plus beta P2 plus gamma by 2 1 gamma mu 2 plus delta by 2 2 gamma mu 1. Okay. Now as we saw in the last class, L minus P1 square is equal to M square will give you beta is equal to 0, right. L plus P2 square minus M square will give you alpha is equal to 0. Okay. L plus P23 square minus M square is equal to 0. That means what? That means minus S23. So if I expand this, what do I get? I get L plus P2 square plus P3 square plus 2 L plus P2 dot P3, right? Am I right? Okay, just 1 minute. Let's do the squaring. So this will give me what? L square plus 2 L dot P23 plus S23 minus M square, that is 0. Now L square is also M square, right? So L dot P23 is basically minus S23. If I put it here, that means I have to multiply with 2 P2 dot P3, right? So that will give me minus S23 is equal to what? Alpha is 0, beta is 0, so I am not bothered about that. So gamma by 2 1 2 plus 3 2, right, plus beta delta by 2 2 2 plus 3 2, right. Now after, I think I am right. Sorry, I am wrong, because I multiplied with, remember I multiplied with 2 P2 3 mu. So these two vanish, these two vanish. Okay, fine. So I got one equation which is gamma 132 plus delta 231 plus S23 is equal to 0. Okay. Now I have also another constraint which is L square is equal to M square. Yeah. Yes, sorry, right, this is 1. Okay. Now if you do this, as we have already seen that square of gamma and square of delta, they will vanish, right. So what I will get? I will get gamma delta by 2. So 2 times 1 by 4 gamma delta S12 is equal to minus M square. Okay, just check if you are getting that or not, then I will do explicitly if needed. So this will give you some gamma delta is equal to what? M square by S12. Okay. Yeah. Right. Okay. All right. So I have one equation like this, and I have another equation of this variety. Okay. So you can see, if I replace it here, I will get a quadratic equation in terms of gamma, right? What is that? That is gamma square 132. I am multiplying it with gamma plus gamma S23 minus M square by S12 231 is equal to 0, right? I combine both the equations. Okay. Now I know, so basically now I have to put okay, fine. Now I have to put that L mu expression here and here as well, right? So that is for the box cut. Okay. Now if I simplify this trace part, it is very easy to see that it will boils down to, that you can easily check, 2 L plus P23 dot L minus P1 plus 2 M square. Okay. Nothing here, just trace calculation. Okay. Now if I simplify it further, M square by V 2 L square plus L dot P23 minus L dot P1 minus P1 dot P3 minus P1 dot P2 plus 2 M square. I am calculating only the trace part. Okay. Now I know L square is equal to M square, L dot P23 is equal to S23 by 2, L dot P1 is equal to 0. So what do I get? I get M square by V times 2M square, 2M square, 4M square minus yes, so 2 is here. Okay, fine. So that is basically, so this is minus S23, so that is basically S23 minus S13 minus S12. Okay. Yes. So this is M square by V 4M square minus M Higgs square. Okay. So now my expression is M square by V 4M square minus MH square 1 over 1 2 2 3 1 L slash P2 slash 3. Okay. All right. Now I have to put this L slash here. So if I do that, what do I get? 4M square minus MH square 1 over 1 2 2 3 1 L slash will be 2 1 2 3 gamma, right? Is it understood? Okay. So L slash is coming from this expression, alpha is 0, beta is 0, so I have only these two terms, right. Now if I put L slash is what? L slash is, in this notation, L slash is gamma 1 2 plus 2 1 plus for delta something, right. Now if you put it here, only this term will survive, okay, because others will be 0 because of angular square. Okay. So now I have 2 gamma, right, because I have a quadratic equation. So I have to take both the solutions. So gamma plus gamma minus, I have to sum over all possible gammas. Okay. Now from this equation it is easy to see what is gamma plus gamma minus, that is minus S23 divided by 132, right. So if I put it back here, what do I get? M square by V 4 m square minus mh square 1 over 1 2 2 3 1 2 1 2 2 3, and this is what? Minus S23, that means 1 2 sorry 2 3 3 2 divided by 1 3 3 2. Okay. So 3 2 3 2 gone. Anything else? Anything else? No. I have done something wrong probably. What is that? Oh no, I have not done something wrong. Yeah, okay, fine. So this is 4 m square minus mh square, this is 1 2, this is S23, S12 plus S23 divided by 1 2 2 3 3 1. Okay. So this is the box coefficient. So simple. Yeah. Okay. So that is how the calculation goes. If you, do I have time? No, I think. Okay. So similarly you can calculate the triangle diagram. Okay. And basically this is not the all box coefficient, because I have taken this color ordering, right, 1 2 3, and I have taken Higgs here. So this is basically what I have calculated. I have calculated this box coefficient of this. Okay. Now Higgs can get attached at this point also, right. So you have two more possibilities. So the full box coefficient is D1 2 3 4, and I know what is the expression for the associated box coefficient plus 2 cyclic ordering of that. So that is all. Okay. No. You just change 1 to 2, 2 to 3, 3 to 1. That's it. Okay. So any questions? Yeah, that I cannot show you on the board. The expressions are large. Yeah. Yes. Yeah. From this expression I can show you how to calculate the triangle diagram. That is also very easy. So this part will be same for triangle diagram also, but this part will be different, because in that case I cannot constrain one of these two, gamma and delta, right. But I can do one thing. So the major part will come from here, okay, because rest calculation is same. Now what I will do to extract the box coefficient? In the box coefficient, say I will not cut this propagator, okay. So that means this propagator is hanging here, okay. Now this propagator is basically nothing but 2L dot P2 when you are applying the other cuts, okay. Now this L slash plus P2 slash is what? That is basically 1 2L dot P2 minus P2 slash L slash 3. I can write it, because I switched gamma mu, okay. 2L dot P2. So you see, it is coming as 1 3. So this is basically what I told, that you have to factorize, you have to do what is that called, partial fraction, right. So this is that part, and the rest part, which is 1 P2 slash L slash, probably this is minus 3, and this is with 2L dot P2, a denominator. So this is basically corresponding to box. Box I have already calculated. So this is my triangle coefficient. That is so simple actually. And in this, for this particular choice of helicity, box is 0. Okay, sorry, bubble is 0. Okay, so that's all actually. Okay. So I think I should stop here, right? Yeah. Fine. Okay.
Some questions.
Yeah.
This is basically, you are calculating an amplitude where all the propagators are replaced by delta functions.
All the propagators replaced by delta functions for box.
For the box, yes. And then you have loop integral. So since it is 4 dimensions, all integrals can be done. D4L can be done.
This is in 4 dimensions, but I have to also calculate the rational.
Yeah. So I mean, for this part, it's like a D4L with a product of 2 4 delta functions, and the solution will give you constraints, and the constraints are substituted in the matrix. Suppose I don't know this method, is it possible to compute by the conventional method also? Just solving these 4 delta functions and substituting in. That will also give, that expression will be very big. So this simplification may not, I just
so you are telling the amplitude I got, that was very simple. If I have a...
So the answer looks very simple.
Because I use BCFW.
So yes. Suppose I don't
know the BCFW. Then also you get this. That I cross verified.
Oh, I see, okay. By solving that.
Yeah. Exactly.
Which is faster actually.
BCFW, I do not have any automated thing. I did it by hand. And basically for this result, it was done by Ochino in 2018 or something. They have a very nice expression actually. Suppose if you have T bar and gluon, n gluon at T, and when all the gluons are positive, T has a nice expression. So I use that basically. But it is also possible to show you how it is coming. And he has a also nice expression when one gluon is minus. So that is known in literature.
Normal simplification.
Yeah.
Otherwise it will be too complicated.
Yeah, I mean, everything doing by hand in a blackboard,
It's not possible.
it's not possible unless your expressions are very small. Very good. Yeah, someone was asking about the BCFW. So the idea I am quickly telling you. Okay. Just give me 2 minutes. So there the idea is basically BCF, Guito, Pagano, they are simplifying the loop diagrams in the low energy limit, and they are producing some recursive relation, and we then showed that, I mean, along with them they showed that these recursive relations can be applied in simplifying the tree amplitude. Okay, how? Basically, suppose you have a tree amplitude and it has some, so all are massless for the time being, what I am telling. Suppose you have two momenta like ki, kj. Now you shift ki to ki tilde in this way, z q. Okay, all mu are hanging around, and kj is basically kj minus zq. Okay, where q is another massless vector. Okay, and you can see that momentum conservation is satisfied, right? Is exactly, yes. So momentum conservation is satisfied, no problem. And if I impose also that kiq kjq is equal to 0, okay, then this is also massless. If ki is massless, ki hat is also massless. Okay, but the point is that this q could be complex, a complex vector. That also you can easily see actually from a nice example. Say you have ki is 1 0 0 and kj is 1 minus 1 0 0. Okay, so I want ki dot q is equal to kj dot q is equal to 0. So what could be the q? Q could be anything of this sort, that will work, right? Also I want q square is equal to 0, then a square is equal to minus b square. Okay, then what q could be? Q could be of this variety, right? So q would be complex. Okay, so when I am shifting this, basically I am making the momenta complex. Okay, now the same thing you can translate it in the form of spinors. Okay, so say corresponding to ki, my spinors are this, right, and corresponding to kj, my spinors are this. Okay, now instead of shifting the momenta, I can equally shift the spinors. So I shift the I spinor like this, z j plus j spinors like j minus z. Probably I am writing it right. Yes, it is right. This is square, this is angle. Yeah. Okay, so here if you calculate, you will see that I have taken q mu is equal to I gamma mu j. Okay, fine. So this is equivalent to shifting the momentum. Okay, now your amplitude is a variable of z, and z is complex in this case, right? So now your propagator is also variable of z, and there can be poles in the propagators. At the tree level, all poles comes from the propagator only, right? Okay, so what does it tell then? It tells if I calculate this quantity, integration of dz on some contour, okay, say 1 over 2 pi is here, so that in the residue I do not have to take the 2 pi. So the residue is then az of say z alpha, where z alpha is the residue, all possible residue. Okay, from here it is very evident that z equal to 0 is a pole, right? So this is basically a0 plus residue, sum over residue of Az where Z is not equal to 0. The pole is not at the 0. Okay, I can write it. Now, if I constrain myself such that if Z tends to infinity, at Z tends to infinity, Az goes to 0, then this integration is 0. Z tends to infinity, Az is 0. This is 0. In that case, A0 is basically minus of sum of residue where pole is not equal to at 0, and A0 is my amplitude, what I want to get. So this is basically VCFW. Okay, so you calculate, so, and pole at propagator, what does it mean? Suppose I have p square minus m square, then pole at propagator means I am making p square is equal to m square, right? So basically if I have a tree level diagram, I can even cut it at the tree level itself, and I will find all the poles and I will sum it up. That is VCFW. That's it, nothing else.
Pole in the Z plane.
Pole in the Z plane. No, pole in the Z plane.
But not the propagator. Not propagator.
No, the propagator is also now complex, no?
Yeah. The vanishing of denominator. Sorry, A of Z is an amplitude that contains the propagator. Then you are looking for poles
at the propagator. Yeah.
Yeah. So for Z alpha you are looking for from the propagator.
Exactly.
Vanishing of the propagator will give you Z alpha.
Will give you Z alpha, and you have to sum them up. That's it. Yeah. And this property, there are many papers to prove this property. Brito, Stefan. No, there is, yeah, there is. So, HI, if it is plus plus, then it can be shown at the large Z limit, Z is varying like 1 over Z. For minus minus it is 1 over Z, for minus plus it is 1 over Z, but for plus minus it is Z cube. So, yeah, so when you are taking this deformation, this is called VCFW deformation. It is not allowed when I is for a plus particle and J is for a minus particle. But that is not a problem, right? Because you can switch the particles if it is plus and minus.
That's an important condition.
Yeah, exactly. Okay. Okay, I should stop now. I have taken 15 minutes extra. Sorry. Okay.
So there will be 5 minutes break, and after that we will gather here and start here.
Yeah. Yeah. Thanks to all. You are very attentive to the organizer. You arranged such a nice school.
They have got work. Inviting is very easy.
No, organizing is a difficult part, I would say.
Credit goes to those. This AMPS
For all scalars. Oh, 5K I don't know. I was thinking about N34 superior mill and all that. There they use. Yeah. Gravity it works. Gravity? Yes. For scalar there is some.
This statement will be true for 1 loop or 2 loop.
No. At the loop level it is.
If A of Z is again a loop contribution. A Z is A of Z is an amplitude. That amplitude is.
So their problem is that here all the, at tree level, I can always say that the pole is coming from the propagators, which are dependent only on the external movement.
Correct.
But there I cannot say that.
I'm not saying anything about elliptic. I could finish few things actually for this tagging. So you're getting it. Okay, so suppose if I compute an amplitude with loops, then you compute some complicated, polylogs in this case, and then those polylogs will be the external momentum. Then again, if A of Z vanishes for Z large Z, then this formula should be similar.
But here A is not defined.
A is not?
L, loop momentum.
Loop momentum. No, suppose I perform this computation.
We add this W menu, which is 1 by 2 pi. Let me just hash T4 psi V power I Q dot psi, commutator of two electromagnetic currents. Okay. And I said this this is not computable because we don't know how the form of J, and even if you know the form of J, we don't know how J acts on this state P. So it's a non-trivial integral because we don't know much about this. Even if you know something, it's not quite straightforward. Okay, but I'll try to do the following thing by relating to what is called T mu nu, which is some simplified version of same thing, but instead of commutator, it's now a time order product of these two currents. Okay, so I work with commutator of matrix element of time order product of two currents, which I denote this by Q comma P. Okay, because this is easy to handle, and if I know how to relate these two quantities, then I'm done. Okay, but these two are related by simply by just calculating some imaginary part of it. Actually, that I'll come back later on. Let's now, instead of looking at this, we look at this expression. Okay, as I said, actually, there was proposal by Wilson, who actually showed that if you have a product of composite operators, you can always express them in terms of certain singular functions in the limit x and y approach, or x minus y is on light cone. You can always express them in terms of some other operators. Let's say this is x plus y by 2 or so. Okay, and then terms which are suppressed. So this is the most singular part. So the series is arranged in such a way that the most singular part appears first, and then less singular ones appear later. So it's like this. Actually, this is how the series looks like. Actually, in the limit x goes to y, or x minus y goes to closer to 0, and so on and so forth. Actually, otherwise this is well defined product, no issues. Only when they approach each other, you have all these complications, and these complications can be sort of pulled out and written it in this particular format. Actually, that goes by the name operator product expansion, OPE. This is what I said. Okay, now I want to see whether a similar thing can be used here, but instead of really just following what Wilson said, let's try whether we can actually get something like this by working in some approximation. So the approximation that I'm going to make is actually assume J mu is electromagnetic current, okay, having the following structure. Or form. For example, I can write J mu like this: psi bar x gamma mu psi, which means actually I assume this current is made up of this fermionic field operators, and it is vector like of this kind. It's very similar to electromagnetic current that you write in QED. Okay, and I assume these psi's are free field operators. And as you can see, this is a composite operator. Well, you can ask the question whether this composite operator also need to be defined according to Wilson, but the answer is no, because this is a well-defined composite operator. It doesn't require anything like operator product expansion. Well defined. Why? Because it's an electromagnetic current, and it has some symmetry that tells you that it's conserved. So any conserved operator, if there are some symmetry of this kind, then often those operators do not encounter any singularities as the points coherence. So these operators are well defined in quantum field theory. Okay, not all operators are well defined, but this one is well defined because this is conserved current. So just keep this in mind that we don't need to do anything with this operator, but the product of these two operators, when if you put in here, they might require some manipulation. For example, if I substitute this T mu nu p comma q in this expression, T4 psi e power I q dot x, so you immediately see that you have these two currents psi bar x. Okay, let me just put, this is x actually, but if you put it here, then it should be psi of psi bar 0 gamma nu. Let me just write down mu, this is mu, psi of 0 p. Okay, this is one composite operator, another composite operator, and this product of this is also another composite operator. In these two, in this composite, this composite operator is well defined. This is also well defined, but it's not guaranteed that the product of these two are also well defined, because there is no symmetry which tells you this is well defined. Okay, so I need to sort of carefully deal with this. So time being, I assume that these are these J's are simple currents like this, and the fields that appear here are free fields, which means there are no interactions. So let's see what this gives you. Okay, so all I need to do is actually I need to compute this matrix element carefully. So I'm going to do this in this following way, because we all know that time order product is simply written as, if you have a time order product of two currents, one at x gamma mu psi of x and psi bar of 0 gamma nu psi of 0. This is easy to express in terms of the propagators using using these well known Wick's expansion. So this is simply product of two currents here, no contraction. Okay, then you will have one contraction. There are two such one contractions. You can contract this one and this one. So two possible ones, one contractions and two contractions. Okay, so let's write down those two expressions. Okay, so the first one will be j mu of psi into j nu of 0, and okay, the second term would be, just write down how it looks like. It is normal order product of psi bar psi into gamma mu times vacuum expectation value of time order product of psi bar of 0 times gamma nu psi of 0, again normal order product, plus the other contraction will be psi bar of 0 gamma nu vacuum expectation value of this time psi of 0 psi bar of psi times gamma mu psi of psi, and then you will have two contractions. Okay, psi bar like this and psi bar like this. Okay, so this is how it looks like. So this first one will be contraction like this, the second one will be contraction like this, and then the last one will be contraction of both. Actually, this is quite simple exercise. So as you can see, you'll encounter two fermion propagators. Okay, all you need to do is actually substitute the propagator here, and let's study the what happens to these propagators in the Bjorken limit. Okay, so for that I am going to use this formula that every one of you is familiar with it, x of 0 psi bar of 0 vacuum expectation value of this is usually called SF of x, which is minus integral d4p 2 pi whole power 4 1 by p slash minus m plus I epsilon e power I p dot x. Okay. This is what you all use. So I put minus sign here. It's not going to matter. So an SF of x is I del slash plus m, which every one of us know, because if you use solution to Klein-Gordon and apply this operator, you will get, SF of x actually. Okay, this is how it's written. And I want to look at everything in the Bjorken limit. So Bjorken limit corresponds to taking psi square close to 0. Okay, which means I want to compute this, propagator, all these propagators in the limit x square closer to 0, which means if I write down SF of x, I need to compute in the limit, say, let's say x square closer to 0, which means I have to compute this quantity I del slash plus m del of x square closer to 0. Okay. Now it's very easy to actually do this exercise. If you notice that delta f of x has has this following a result, because it's a free field theory. This integral is the delta f is computable explicitly in terms of this x. The Fourier transformation can be done quite straightforward way. So all you need is actually you have to just substitute this expression. So this would look something like 1 by 4 pi times I, 4 pi square times I times x square. This is minus I epsilon. Okay, like here you have plus I epsilon. In Fourier space it will become minus I epsilon. Okay, this is how it would look like, plus a less singular part. Okay, I will not write down what those terms are. They are proportional to some log square and things like that. Okay. Now if you compute this SF of x, all I need to do is actually take a derivative of this function. As you can already see that the propagator that we have encountered here in this product of commutator is proportional to this Feynman propagator delta f, and this Feynman propagator in the limit x, this on the light cone looks like this, which you can see that as a pole at x square is equal to plus I epsilon. Okay, so it's a singular function. Okay, so this is what Wilson actually anticipated in any quantum field theory. If you have a product of composite operators, you encounter this kind of a singularities actually. So if you calculate SF of x, it will be simply minus x slash by 2 pi square times 1 by x square minus I epsilon whole square, and I am leaving out higher order terms. Higher order means they are less singular terms in this, because it's the singularity is ordered in the terms are ordered in such a way that the most singular part appears here and the less ones are appearing later on actually. So now all I need to do is actually this time in the time order product I need to put this two functions and then write down all this. So now the time order product looks like T of j mu of psi j nu of 0 now looks more like So I'm also going to sort of concentrate only on the second and third terms, simply because if I really want to compute W mu nu or T mu nu, these two first and last terms actually will have no role to play, because since it is about scattering and this will be proportional to some identity operator, the transition matrix element will be just simply will be just a constant, won't be having any interaction with the photons. Okay, this will completely drop out if you substitute back into this expression. Actually, you can also easily see this if you write down Feynman diagrams corresponding to this. So the only two terms that will contribute to this W menu are the second and third terms. So let's only concentrate on second and third term. The other terms are called disconnected. Disconnected means they don't participate in the scattering reactions. Okay. Product. First term is already normal ordered. That is not going to contribute to any scattering events actually. This normal ordered operators actually. It basically it completely will decouple from your normal order means just the entire thing just drops out actually. Okay. So now I am going to sort of restrict myself to only the second and third term, which looks something like this actually. The second term, third term would look like psi bar of psi gamma mu times, I'm just going to write this is minus I minus x slash by 2 pi square. Okay, so this is something like this, 1 by x square minus I epsilon whole square gamma nu psi of 0. This is psi. This is psi slash. Okay. Okay. So this is. So now you can already see that there's some nice thing is happening here. Namely, the second term would be psi bar of 0, gamma nu. This will be minus I, psi slash by 2 pi square, 1 by psi square minus I epsilon whole square into gamma mu psi of psi normal order product actually. So and then I'll keep those terms, but eventually those things will not contribute to my scattering reactions. Okay. Fine. So let me just proceed. So this structure actually reminds you of what Wilson had proposed. For any generic situation like product of composite operators can be arranged in terms of some local well-defined local operators multiplied with the singular coefficients. Okay, this is apparent from here because if you really look at it, this is just a function, singular function as psi square goes to 0. This is also singular function as psi square goes to 0. The remaining part is psi bar, psi, gamma mu, gamma nu psi is actually this local operator that he has written down here actually. So this is simply an operator product expansion that we can derive for free field theory. Okay, where you know everything about the operators, hence you can actually show that what really happens when these two currents approach each other in space time on the light cone. Okay, so this is kind of a derivation for OPE. Okay, but I have not proved that this remaining term, these operators are well defined. Okay, if I calculate matrix element of them, they should be well defined actually. That's the point. Okay, but I have separated out singular part very nicely from this. Okay, this is something that you can do. Now I'll proceed and see. That's not the only goal to to show this is OPE, but I want to sort of calculate W menu. So I'll have to proceed. Yeah.
There won't be any negative biasing?
Negative psi. This is a plus actually. That's what I've written down here. Because of that you have to one is actually I del slash You can see this is because of 0 xi, no? 1 is, this is xi 0. It's time ordered product, but if you use translation invariance or whatever, you can show that it is. Because it is, you can see the sign here actually, no? It is not even. So if you change psi to minus psi, this is even, this changes sign, no? Right? So that's the reason actually. Okay, now how do I simplify this part? Okay, so I'll use this identity. There is something called gamma mu, gamma lambda, gamma nu. As I said, if you have more than 2 gamma matrices, you can always express them in terms of one gamma matrix or gamma mu, gamma phi. So there's a very famous identity. This is sigma mu lambda nu rho plus I times epsilon mu lambda nu rho times gamma rho, gamma, this is gamma phi, this is gamma rho. Okay, here this sigma mu lambda nu rho is actually some combinations of symmetric tensors rho minus chi mu nu chi lambda rho plus chi mu rho chi lambda nu, and this epsilon mu nu is Levi-Civita, fully antisymmetric tensor. That's all about this quantity. So which means that I can actually write this product of 3 gamma matrices as sum of 1 gamma matrix plus 1 gamma phi gamma matrix. Okay, there is some advantage in doing so. Okay, I'll just write down how it looks like. So this left hand side looks like now psi bar. Let me just simplify and write down I times x lambda divided by 2 pi square. X is, my notes contains x square, so that's the problem actually. Mu lambda nu rho psi of 0 minus psi bar of 0 gamma rho psi of psi. This is first term, and then the second term is again plus psi lambda divided by 2 pi square, psi square minus I epsilon whole square, epsilon mu lambda nu rho. You have another operator which is psi gamma rho gamma phi psi of 0 plus psi bar of 0 gamma rho gamma phi psi of psi. This is another operator. So I have sum of 2 terms. Again, this will remind you of what Wilson said. The singular part you call C. This C is that I have written down, and then the operators. Okay, and these operators are supposed to be well behaved on the light cone. Okay, it should not contain any additional singularities if I compute. Okay, that was the idea actually, and it is indeed so. If you really substitute and calculate these matrix elements in free field theory, for example, because I pulled out all the singularities as psi square goes to 0 limit actually. Okay, so because it's obvious, because I said this current that I written down here, because it's conserved. Okay, even if they are defined in the same space-time point, it does not need any additional renormalization to make it finite or anything. It's already well behaved, well finite. So that's the idea behind this. Okay, now all I need to do is actually I need to relate this T mu nu to this. Okay, That's not difficult, because it's easy to show that if I write down, commutator of these two currents and the time order product of these two currents, you can show that they are related by, some imaginary part. Like if you calculate the imaginary part of this quantity, it will turn out to be just a commutator. I'll not derive this. This can be done in a very straightforward way. So I'll just write down only the relation between these two. Okay, this you can try it on your own. Okay, basically, you'll have to again, sort of expand this commutator as well as time order product, and try to see you can go from one to the other by making certain transformations. So what you do is actually you calculate 2 pi I times T mu nu with Q0 plus I epsilon and T mu nu Q0 minus I epsilon. It is basically taking, it's called computing the absorptive part of this time order product, a Fourier transformation of time order product of these two currents. Okay, I keep this protons as it is, because in all these manipulations, okay, you will see that this proton state is essential, because this decides, the proton momentum tells you about the kinematics of this. Okay, some terms will be non-zero, some terms will be zero, simply because the presence of this proton actually. Okay, so you will have to be careful. You cannot just drop this proton states and then do manipulation. So you need to keep them as it is. Okay, yeah.
In some earlier lecture, you just said that if you open that commutator, then
One of the second term is 0. Yeah.
So if the second term is 0, then aren't the two W mu nu and T mu nu just equal?
They are not equal, because the T is actually time order product. No, this is T is actually theta of x0 plus j mu, sorry, psi 0. It's okay, no, because they are not equal actually. So you need to really take imaginary part. You do this kind of manipulations actually. You're right. The second term is 0 identically. Okay, that happens in here also. If you calculate this quantity, no, it's not 0, because there will be two terms. For example, there is a theta function, psi 0 here with the two operators. Let's say jj. Another term which is psi 0 jj, and you can show that by taking q0 plus I epsilon, q0 minus I epsilon, you can if you perform this integral over let's say 0th component of this, you will get some 1 over terms like this actually, 1 over some q0 plus something plus I epsilon and minus 1 over q0 blah 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 terms minus I epsilon, and then the difference will be it's just as Satyajit was showing this. You can write this as a principal part plus delta function, and this is also principal part plus delta function. The difference will be proportional to delta of something. So that's how you proceed actually. This exercise can be done. It's not very complicated. Okay, now all I need to do is actually calculate the absorptive part of this quantity. Now the absorptive part will come from this, this psi square minus I epsilon, psi square minus I epsilon, these terms. So all I need to know is actually what is the absorptive part. Okay, because the principal parts cancels. So I'll just write down what those terms are. So all you need to do is actually write down psi square plus I epsilon equal to principal part of 1 by psi square plus I pi delta psi square. Because it's minus I epsilon, you need to put plus I pi here. Okay, so for I powers actually you need to differentiate on both sides actually. So the same formula would work. The only difference would be this: for a square, you just differentiate with respect to psi square, and then you get an higher powers of that denominators. So you can still use the same formula, to compute this. For example, if I want to compute nth power, let's say this nth power, this will be again the principal part of psi square power n. Okay. The only difference is actually some complicated functions. Let's say I don't care because I'm going to subtract this. So this part I will not worry too much. Okay, but if you look at the second term, it will be 2 pi I times minus 1 power n minus 1 divided by n minus 1 factorial, okay, delta n minus 1 psi square. So it will be simply this nth n minus 1th derivative of this. Okay, if I calculate this n, so it is more like that actually. So now you can substitute this imaginary part of this, and you can straight away write down what W min is. So you can show that epsilon 0 commutator is simply x lambda by pi psi lambda delta 1 psi square sigma mu lambda mu rho times O rho x comma 0, okay, plus minus this is I by pi psi lambda delta 1 psi square epsilon mu lambda mu rho O rho 5 x comma 0. This O rho x comma 0, O rho phi x comma 0 are basically these quantities actually. So I can just call it as this is O rho x comma 0, and I call this entire term as O rho phi x comma 0. This is my definition. So it simply boils down to this simple expression. This is just this what's called sine function, which everybody is familiar with, psi 0 by psi 0 or whatever. Just overall. Psi, yeah, here. Sorry, because my entire notes as x, so when I copy I make mistakes. Okay, wonderful. So this is what you get actually. Now, all I have done is actually I have calculated commutator of two electromagnetic currents in the free field theory, and I took the limit, that psi square is closer to 0. And I have dropped all those terms which are less singular in the limit psi square goes to 0. Okay, so this is the most singular part of the commutator of two electromagnetic currents on the light cone. Okay, and less singular parts I'm not interested, but you can keep them if you like it, but they will give contributions which are suppressed in the Bjorken limit. That's the whole idea. Okay, let's keep it. Okay, is this clear to everybody? So Bjorken limit means large Q square, which corresponds to space-time separation, or light cone separation is infinitesimally small. Okay, that's the connection between these two. Okay, so let's proceed and see. So in physically also, you can see that when you are doing deep inelastic scattering, large Q square corresponds to really probing some product of currents at very short distances. Okay, that you want to see what happens at very, very short distances. Okay, and I want to make a remark here that this it is just what Wilson proposed for composite operators. This is also composite operator, product of composite operators, and you can clearly see that these are singular parts actually. These are delta functions highly known, singular quantities. Why I comes? Is it?
The first line does not have any I, second line has I, but both is same complexity.
I comes because because you have this epsilon mu nu lambda sigma, no, this gamma phi and things like that. Oh, there is no I here actually. Okay. Let me just check actually. Maybe I have made some mistake. Okay, I'll check it actually. Maybe there is something that I have missed. There should be I definitely, and in the first term maybe it's absent. Maybe I just first term maybe it's absent. That is true. Okay, let me just check whether this first term has it or not. Okay. Because this epsilon tensor comes with I, sigma doesn't come with I, so some i's are cancelled already. Okay, so that's okay. Now I have to sort of take this and substitute here and see how W many looks like actually. What does this tell you actually? So now I'll do a very simple algebra which is not difficult. So W many will be Fourier transformation of these two currents. So I'll just have to substitute. I just have to bring this here and put it. Okay, I'll copy that part here. And all I need to do is actually I need to sandwich between proton states. That I need to be careful. So this entire thing should be sandwiched between two proton states. PP, I'll put it here actually. Okay. So the P will only act on, or this operator will only act on this P. The remaining terms are just simple functions. So you can pull out. So this entire thing will be proportional to these singular functions times matrix element of either this operator or this operator. Okay. So these terms that appear inside will have some singular functions times this quantity, another set of singular functions times this operator matrix element. Okay, this you can do. Now this integral can be done provided if these operators are independent of psi. With this psi dependency, I won't be able to perform this integral. Right? Is this clear? If this operator is function of psi, then I won't be able to do this integral. So I'll have to somehow manage, get rid of this. Okay. As I said, the operators are well defined. Okay, in psi square going to 0 or psi goes to 0. It is a well behaved person. So all I can do is actually I write all this P as sum over n 1 by n factorial, n is equal to 0 to infinity. Okay. Psi mu 1 psi mu 1 times del mu 1 del mu 1 whatever rho or gamma phi is generically actually. For example, for rho this my psi is equal to 0. So what I have done is actually I have just calculated the Taylor expansion of this quantity around psi is equal to 0. Okay, I can manipulate the way I like actually, because this is a well behaved function. I can make a Taylor expansion around psi is equal to 0. So it's just a simple Taylor expansion, and this is a set of derivatives acting on O and evaluated at psi is equal to 0. So this is again some composite operator with a string of derivatives sitting here actually. Okay, and now I have sort of pulled out all the psi dependency. Now I can pull out all the psi's outside this matrix element. Okay, so that's another simplification that I can do. So what it does is actually this allows you to perform this integral. Okay, simply because you can actually pull out all the dependency on Okay, I'll just write down carefully. So if we substitute there, it will be just sum over n equal to 0 to infinity. Okay, and let me just write out carefully what I have written. So 1 by 2 pi square, it looks something like this: d4 psi e power I q dot psi times x lambda epsilon x psi lambda epsilon psi 0 times delta 1 psi square, and then you can have this times sigma mu lambda mu rho summation over n is equal to 0 to infinity 1 by n factorial psi mu 1 to psi mu n. Okay, then this operator matrix element P del mu 1 del mu n O rho psi 0 evaluated psi is equal to 0. Okay, something like this. So you can see there is this operator matrix element where you don't have any psi dependency. So I can pull out this entire psi independent quantity outside this integral, and the remaining ones are actually just Fourier transformation of delta functions actually. Okay, this is the first term. Similarly, you can write down the second term also. Let me just restrict myself to only, let's say, symmetric part of mu nu, because whatever I do will go through for the antisymmetric part also, because as you can see gamma mu gamma phi comes with epsilon, which is antisymmetric in mu nu. So only restrict yourself to mu nu. Whatever I do will go through for the antisymmetric part. So this expression is 1 by 2 pi square I can pull out, and I can also pull out this sum over n is equal to 0 to infinity 1 by n factorial times this entire matrix element P del mu 1 to del mu n O rho psi 0 evaluated at psi is equal to 0 P. So this is completely independent of this integration variable. Okay, the remaining term will be 1 by 2 pi square multiplied by d4 psi e power I q dot x q dot psi lambda epsilon psi 0 delta 1 of psi square, okay, times product of this. Okay, this is more like a tensorial integral containing string of the size with indices mu 1 to mu n. Is this clear? Okay, so this some operator matrix element multiplied by some calculable function actually. This function contains this delta 1 xi square, which is the singular part. So if you know how to compute this integral, then I am through. Okay, so let's see how we can actually do this integral. It's straightforward again. If I do little manipulation with this matrix element. Okay, so now you see this is a matrix element of rank n tensor. Okay, sandwich between proton state. So let's find out what is the most general rank n symmetric tensor that you can write down for this. Okay, like in previous classes we were doing these manipulations with this. So if I know how to write this del mu 1 to del mu n comma 0 rho at psi is equal to 0 between proton with the vectors available in this matrix element, then I am through. So what is the most general expression that you can write down? It has to be rank n plus 1, and it should be fully symmetric with respect to mu 1 to mu n. So it's a rank n plus 1, and it is fully symmetric with respect to all n indices. That's all I need to do. So I'll write down all possible things. So one possible this thing is actually it's proportional to p rho. Dimensional counting tells you that the only vector that I can write down here is actually p mu. I can't use gamma mu, I can't use s mu, I can't use anything else. So it's only, if at all it is a function of something, it has to be a function of this momentum p, because that's what you are computing between two proton states, p rho. And then it can be functions of p mu 1, p mu n. Let's say this unknown coefficient is actually for me, because it's n quantity, so it can be a function, let's say a n. The invariant here is p square. Okay, this is one possible combination, and here I can say it is fully symmetric with respect to mu 1 to mu n. So I put some symbol like this. You can also have term where, you can also have term, this is not the most, there can be more terms actually, because you can write down a term like bn of p square, okay. You can write g rho mu 1, okay, fully symmetric with p mu 2, p mu n with bracket like this. So you can write, compromise one momentum p, instead of that you can put g rho mu 1. This is also a rank n, fully symmetric with respect to 1 to n, and so on and so forth. Then you can have another term with 2 g menus, 3 g menus, and 4 g menus, and so on and so forth. Okay, and we also make sure that the cost, this coefficients a, b, etc., they are dimensionful, and the dimensions are adjusted in such a way that the dimension of left hand side is equal to the dimension of right hand side. Okay, that can be done in a systematic way. That means the right hand side in principle can be expressed in terms of this again string of proton momentum and proton momentum combined with 1 g menu, 2 g menus, and so on and so forth. Okay, the last term in this series will be just a product of all g menus with the dimension of this coefficient will be the dimension of this operator itself. So that is how you can write down. Now again you are stuck. If you have infinite number of terms, if there are n such things, there will be large number of such combinations will be there, and it's meaningless to actually proceed with this if you have n. But again this Bjorken limit helps us actually, since you are interested in this Bjorken limit, and that helped us to drop many terms. We can again see whether which is the dominant part in this expansion. Okay, this is just a tensor decomposition. I have not used any limit. Okay, now it's easy to show that if you take each one and substitute and see which one is the dominant term. Actually, you will find that the most dominant contribution in that limit would come from this part. Actually, it's easy to show how is if you take all p's here, not g menus. Okay, let me just go the other way around. If I take any other term, any term other than the first one, g, if I multiply 2 g's, what will happen? If I multiply 2 g's, there will be product of 2 size. 2 size are they're close to each other. That means it is proportional to psi square. We are dropping terms which are proportional to psi square because we are looking at leading contribution in 1 over psi square. So any term that other than this would always be suppressed by 1 psi square. So it will be less singular compared to the first term. So the most dominant contribution is this particular term. Is this clear to everybody? Okay. So I can ignore this rest of the terms and keep only this part and substitute back here actually. So if I do this, then I will get the following expression. So what I get is actually substitute. So I substitute here. So my W menu will be 1 by 2 pi sum over n equal to 0 to infinity 1 by n factorial this operator, all the p's will be clubbed together, and then this will become, I don't know, there are too many 2 pi's hanging around. Yeah, there's 2 pi, I don't know how 2 came. Anyway, so this is more like an of p square, the dominant one actually, in the Bjorken limit. Okay, so I will be, combining this with p, so it will be integral d4 psi times e power I q dot psi, and then this will be psi lambda epsilon psi 0 times, let's say, p rho. I can pull out this p rho here, okay, and psi dot p whole power n, correct? This is what I get actually. And then delta psi square times sigma mu lambda mu rho is what I get at the end of the day. Okay, good. So far so good. Now I need to perform this integral. This is again kind of a disturbing factor. So what I am going to do is actually I am going to define a function called f of all I can do is actually have this 1 by n factorial a n of p square, okay, and psi of x I dot p whole power n. You call this summation over n is equal to 0 to infinity. I call f of x psi dot p. Okay, this is my definition. So I can actually combine all these n dependent parts. There is sum over n factorial a n of p square, and this psi dot p power n, I call it as this. Okay, just to manipulate this integral. Okay, so if I do this, this will be 1 by 2 pi. I think it's 2 pi whole square because I've separated out by 2 pi whole square integral d4 psi. Okay, and then all AP square, everything is gone, and then I will have e power I q dot psi, and then you have this psi lambda, okay, p rho epsilon psi of epsilon of psi 0, okay, and delta of psi square and f tilde of psi comma p. Okay, so just a small manipulation that instead of keeping this summation over n factorial with these factors, I just call them as f tilde of psi dot p. Okay, delta 1 of psi square. Very good. Yeah. Okay. Again, I have this dependency on this psi dot p of this function. So again, I won't be able to do this integral. So what is the clever way of performing this integral? If we have a function where I have this psi dot p, the clever way of doing this integral is actually you just write down, sorry, this is f, no, this is f. You write down this as some Fourier transformation of some another function, let's say. Okay, if I write this as, let's say, integral dz e power I z times psi dot p into, let's say, f tilde of z, okay, then I can pull out f of z and you can perform this integral. So this can be written as 1 by 2 pi square integral dz f tilde of z times an integral. Okay, there is some sigma mu lambda nu rho I missed actually, so keep that also. This is d4 psi e power I q dot psi, and this, because of this Fourier transformation, you get z times psi dot p, okay, times this whole lot of, this z lambda p rho epsilon psi 0 delta 1 of psi square sigma mu lambda nu rho. So what I have done is actually, keep, sort of improving so that you can perform this integral. That's the goal actually. Otherwise, if you leave it at integral stage, you don't get any interesting physics out. You'll see that, all these manipulations really help us to actually get some nice looking formula. Okay. Otherwise, I could have stopped there itself. Everything is there. So manipulation that I have done was actually that I could manage to sort of pull out this psi dependency out of this operator matrix element. That's the first step. So Summa matrix element comes out. Even after that, I end up with this psi dot p power n, and that stopped me from doing this integral, because there is a dependency on this a n times this n, so it's complicated. So you can manipulate this by writing this summation over psi dot p as some function f of p, because obviously it's a function of psi dot p, and that you write it as a Fourier transformation of over f tilde of z. Z is some Fourier component of this psi dot Fourier conjugate of this psi dot p. Now if you do this, then you can manage to pull out this this entire function outside, and all the dependency on psi dot p will be in the exponential. Now you see this integral is calculable because it does not contain anything that is unpleasant. Everything is function of only psi. So this integral can be done in a straightforward way, because this is d4 psi e, it's a Fourier transformation. This entire thing can be written as I, if I pull out psi, this is q plus z times p. Okay, this is psi dotted with q plus zp exponential, and this is just z lambda epsilon zeta 0 xi 0 and then delta 1 x xi square. This is integral that is is doable actually. So now I just have to just perform this integral. I'll just use some identity, then I'll show you what it is. Mu lambda nu rho times p rho. Okay, this comes out nicely, and then you have this integral over dz f tilde of z. Okay, so what is the answer to this integral? The answer is actually epsilon of q0 plus z p0. Okay, and then because you have some x lambda corresponding to x lambda, you have q plus zp lambda. Okay, this is a Fourier transformation, and then 1 by 2 p dot q times z times delta of 1 minus x Bjorken by z. This is what you get actually. So beautiful actually. So this delta function, this first derivative of delta function, if along with this exponential, if you integrate over d4 psi, just reduces to one simple delta function, because one derivative this is the derivative of delta function. So you expect that the answer will be proportional to delta function without a derivative. Okay, and that allows us to actually perform this integral and write an answer which has no integrals at the end of the day. Okay, that means all the integrals can be performed by simple manipulations like this actually. Okay, don't give up, actually, that's the message. So at various stages you see actually there is, abstraction, and you start see whether what is the most dominant contributions and all I did was actually simple manipulation. One is actually just a Taylor expansion here. Two, I calculated this matrix element of the derivatives, that is step number 2, and step number 3 is actually I went ahead and computed the matrix element. That means I parameterized, and I knew that not all of them would contribute, dropped everything except the first one, that's the most dominant one, substituted here. Still I had this term xi dot p power n, and I had to proceed. The only way to proceed is actually I call this the summation of this quantity as some function, Fourier transform it, substitute here, do the integral, and this integral is this. Now you get only simple delta function. This delta function integral can be performed because z is equal to x bj is the answer actually here, this answer to this integral. So the entire integration can be done if you use this Bjorken limit. Without that you cannot proceed even a single step actually. So okay, so the final answer for this W mu nu, you will find that this is okay. Just I will write down this integral dz minus infinity to plus infinity f tilde of z times some W mu nu of p comma q into delta 1 minus x bj by z. Okay, x bj. How is capital P is actually momentum of the proton, no? So q square by 2 p dot q is x bj, no?
Okay. By doing that integral?
I'm not doing an integral actually. See this integral. Okay, what is that integral actually? Let me just write down, maybe it will be clear. So you are performing this integral. The integral is actually integral d4 psi e power I xi dot q plus zp, right, over psi lambda epsilon xi 0 delta 1 xi square. This is your integral. Okay, the answer to this integral, as I argued out, it will be proportional to a single delta function because it's a derivative with respect to this. Okay, so this Fourier transformation will actually kill one of them. The answer is actually epsilon q0 plus zp0 q plus zp lambda. Okay. So you want the answer to the integral, or yeah, so there is a factor 2 here. Okay, and then you have delta of q square plus z square p square plus 2 p dot q z. This is your answer to this integral actually. Okay. And this comes because you can always sort of remove this xi lambda by differentiating this integral with respect to q, right. If I differentiate this integral with respect to q, you get xi lambda. So you can actually pull out this xi lambda at the expense of writing down, or remove this xi lambda at the expense of writing down a derivative operator acting on this. Okay, and after computation, if you apply the derivative operator, you get this quantity plus this delta function actually. That's how it comes actually. And this delta function is simply, if you work out this, it will be delta of minus q square. Q square is minus q square. I ignore p square because in Bjorken limit this is 0, and then you get 2 p dot q z. Okay. Now you can pull out 1 by 2 p dot q times z, or keep z here. This will be minus q square by what 2p dot q. Okay, this is plus z, right? This is a Bjorken, no? This is Bjorken j. If I pull out j also, then 1 by 2 p dot q z will be, this is minus x bj by z plus 1. This is 1 minus x bj. This is how you get this delta function. Okay, so 5 minutes, I'm through actually. Okay, now you see that, if I just do this integral, this w mu is simply, that second rank tensor that I wrote down, expressed in terms of pq again. Okay, so that's it actually. Don't have much to say beyond this at this point actually. So w mu is like, this minus g mu plus k mu q mu by q square and so on and so forth. Okay, that is this written in terms of p and q. Okay, if you perform this integral, you will get something proportional to f of x p j with this, with w mu here. Okay, wherever z comes, you will have a x p j. Wherever z comes, you will put x p j. Okay, this is roughly what we which I promised to show, that if you compute this, or if you assume that this entire scattering is taking place in this particular kinematic setup, Bjorken limit, then the scattering cross section actually, or what w mu or the structure functions, they scale as x p j. There is no q square dependency, as you can see here. Okay, there is no f does not contain any q square dependency. This is what Bjorken showed using very very complicated current algebra techniques. Here we make some some approximations like free field theory and so on and so forth. Bjorken did not assume anything, just use current algebra and try to show that these structure functions, they scale as scaling variables actually. Okay, and I did not show how the pattern model emerges, but if you carefully look at it, I can actually drop many of the things in between, and try to stick to some approach where I don't have any expression for currents and so on and so forth, by just replacing all my this currents by just writing down j mu of psi, j mu of 0 as some over ci xi square oi of 0. Okay, this is, if I assume this and I demand that this is the most singular part, singular, as xi square closer to 0, okay, and I substitute this in my original w mu expression and try to manipulate the way I manipulated here, without really worrying about what these operators are, and then I can again end up with exactly the same result, where this f will be simply, so if you go back and look at what this f is it f or f tilde? It's f tilde. So f tilde is actually f tilde is Fourier transformation of, I have written down something there actually, f of f tilde is f d of psi dot p times e power x b j into psi dot p times f of z, f of psi dot p. Okay, this is your definition of your f tilde. So you can see that if I actually substitute back this f of psi dot p, which is again this expression, f of psi dot p is sum over all a n's actually. Now you can see that it is again an integral over psi dot p e power I x b j into psi dot p times sum over n 1 by n factorial times a n of p square, okay, and psi dot p whole power n. Okay, so you can see that it is basically a Fourier transformation of you know a function which is psi p power n actually. Okay, so this is something like sum over n is equal to 0 to infinity 1 by n factorial a n of p square times an integral over d psi p e power I x b j psi dot p times psi p power n. Okay. Correct? This is this expression actually, f of psi. Now you can do a clever trick. If you calculate, this, if you want to calculate what this a n, all I need to do is actually, I mean, either I can actually take an nth derivative with respect to x p j, will give you, the answer to the integral, or I can show that if I calculate this quantity 0 to 1, x b j power n minus 1 f tilde by x b j. Okay, if I perform this integral on the left hand side, then you will pick only one term where small n is capital N minus 1 actually. So it will be proportional to just simply a n minus 1 of p square. Okay, so Mellin moment of the this pattern distribution functions are nothing but the matrix element of this local operators actually. So basically I want to just show that you must be hearing Mellin moments of structure functions or PDFs and things like that. Actually they are nothing but the matrix elements of certain local operators. This a n is just the matrix element of this the tensorial operator between proton states. Okay, and that is one thing. So you will see in other theories also people have invested on this, studying operators in quantum field theory, particularly in conformal field theory and things like that, and they study exactly the similar kind of operators. Okay, and the operators are actually classified in terms of what is called twist. In this context actually any operator, tensorial operator, can have two characters, the standard one, the mass dimension, the other ones are actually rank and spin. Okay, and the difference between rank and spin of a matrix of an operator is called twist. Okay, and if you look at the twist of this operator, okay, for this particular operator it's a twist 2 operator actually. Okay, because its dimension is n plus 1 and rank is n, so it is difference is actually 2. Okay, this is so that because this O is actually psi bar psi, so it's of dimension 3, so it is n plus 3 minus there is rank is n minus 1, sorry, n plus 1, n plus, so this is actually 2, so it's called it's called twist. This twist of the operator is 2. So the way it is organized is actually it is organized in such a way that the smallest twist appears first and then so on and so forth actually. So there are contributions which we dropped, they go by the name higher twist operators actually, higher twist terms. Okay, that's one thing that you can keep in mind, because this is an opportunity to tell you what are those. Number 2, I'll finish it in 2 minutes, gone. And then the Mellin moment of the structure functions are nothing but the matrix element of these operators. So there is a operator definition for this, this pattern distribution functions that people talk about. They are nothing but operator matrix elements of, between proton states like this actually. Okay, there is a operator definition for all these pattern distribution functions. The picture that Feynman and Bjorken talked about, that if you collide an electron on a proton, in some particular limit, then the proton looks like a collection of point-like objects weakly interacting, and you can associate probability density to each of those point-like particle. That probability density that Bjorken and Feynman and all visualized, they are nothing but the operator matrix element of some local operators, okay, between proton states. Okay. So there is a one-to-one correspondence between. So in field theory, you can actually define them, in terms of some well-defined matrix elements of operators, local operators. Yeah, I think I stop here actually. So there is this connection between what the pattern model tells and what the field theory tells you about these things. Okay, so I stop here. Thank you. Anurag is around. He is outside. We are going to call him.